Hello guys, so we have a question from 2019 mains, and in this question they are saying the compound for formula A2B3 has a HCP lattice. HCP matlab hexagonal closed pack lattice, and just to quickly help you understand what kind of a structure it has, so it has a hexagon on the top, then it has three particles in the second layer, and again in the bottom layer it has the same hexagon repeated at the bottom like this. So these three particles lie completely inside the unit cell. We also have particles at each of these corners, and we have one particle at the center. The same story goes over here as well. We have six particles like this, and one particle at the center, and there are these three particles which lie completely inside the plane. So this is what would actually look like a regular HCP kind of a structure, right? So now they're saying that in this kind of a structure, the atom forms an HCP lattice. What fraction of the tetrahedral voids is occupied by the other atoms? What fraction of the tetrahedral voids is occupied by the other atoms? Now, here something we need to understand is, first of all, what is the effective number of particles? Effective number of particles in one HCP. We should first find that. What is the effective number of particles in one HCP? So we know that these three particles are completely inside. So we have to count all of them together. So there is a +3 over here. This and this one will contribute half of their volume, because half of them will be taken up by the other hexagonal unit cell which is going to be below it, and here the one above it. So that is why this one is going to contribute just half of its value here. So this is plus half, and this is also plus half. So that's another thing. And then there are 12 of these. If you see 6 on top which are at the corners, and 6 more which are over here, 12 of these. Now all these 12 are contributing 1/6 of their volume to one unit cell. How can I be sure of that? If you take this one for an example, so you have this one unit cell where it is contributing, but again there could be another unit cell which would be like this, where it is going to be contributing its uh, volume, and there's going to be another unit cell which is going to be over here, where it is going to be again be contributing its volume, and then there are going to be three on the above layer as well, where it is going to be contributing its volume, and there are going to be total of 6 such unit cells where this same particle is going to be used, and therefore the 12 particles which are at the corners each are just contributing 1/6 of their volume. So this means that there are two particles effectively coming from the corners, there are three particles coming from the center, and there is half plus half, which means one particle coming from the centers of the faces at the top and the bottom. So the total becomes 6 particles. So effective number of particles in an HCP is 6, and this is a good number to remember. A lot of times people don't know this number, and that is the reason why I just showed you how it comes out to be 6. Now once you know what is the effective number of particles of HCP, the next thing is, can we find out how many tetrahedral voids it would have? So the answer is it's going to be double of that, which means 12. That's the number of tetrahedral voids it would have. Having known this and this, now we are in a position to solve this question by again trial and error method. The reason why we have to do trial and error method over here is because the options have different conditions. So let's look at the first condition. In the first condition, they are saying HCP lattice is made up of A. So if HCP lattice is made up of A, the effective number of particles you are talking about for A in the HCP is 6. And 2/3 of the tetrahedral voids of B are occupied. So B is 2/3 of the tetrahedral voids. There are 12 in all. So that gives you 8. So the formula for this compound in the first option should become A6B8, which basically means A3B4. Is that the formula we are looking for? The answer is no. So the first option is wrong. Even if you reverse it, will that be an answer A4B3? The answer is no. And therefore the last option also can be eliminated over here, because it was the same conditions, just A was interchanged for B. So first is gone and fourth is gone. Now let's look at the second one. In the second one, you have HCP for A again. So A is going to be 6. And one third of the tetrahedral voids have been occupied. So B is one third of 12. That means 4. It means it is A6B4. But if it is A6B4, the molecular formula in the simplest whole number form would be A3B2. And again, that's not what we want. So, but we do want its reverse. We want A2B3, and therefore this would be the correct one. Why? Because in the third one, you just have B as the HCP, so that's going to be 6, and A is one third of the tetrahedral void, so that's going to be 4, and therefore it will be A4B6 or A2B3, and that is what we are looking for. Hope you have understood the solution. Thank you so much.